This is further stats 2 from 2019. So the first question then is talking about the a machine making yogurt pots with a weight of 505, or mass, I guess, of 505. Got a sample here with all these masses here. Got a standard deviation of this. Find the confidence interval for the weight, for the mass again, or weight. This is incorrect of them, right? This is just straight up incorrect of them to say weight u grams. That's just wrong. Anyway, um, yeah, shame on you, Pearson Edexcel. To do this, though, what we're going to do is we're just going to say, well, the mean of the sample is this, just add them all up, divide by 8. We can look for in the normal distribution table, we can see very clearly, or you could do this in a calculator, I guess. You could see that the Z value is 1.96 for, we're going to do a two-tailed test, of course, because it's a confidence interval, so we want the lowest and the highest, so 2.5 either way, which is this value. You could actually just memorize that value since you see this a lot. And then the formula is just the mean plus minus the Z value for whatever the percentage that you're doing is, times by the standard deviation divided by the root of n, the number in the sample. That formula is given on page 121, just in case you're interested. You get this, and that's not two decimal places, but I don't care. You know, they've done this, so I can do this, and we're all just wrong. Two wrongs make a right, don't they? Anyway, comment on whether the machine is working properly. Well, the mass, or the mean that it should be, is 505, and that's well within the confidence interval, so we'll just say that it's working fine. Then state the probability with that a 95 confidence interval that mu won't fall into it. Well, that's just 5%. That's what a confidence interval means, right? 95% of the time you'll be in it, and 5% you won't. So yeah, that's just 5%. Without carrying out any further calculations, what would we do if the standard deviation was unknown? We would have to come up with a unbiased test statistic S for the standard deviation, an unbiased estimator S. And then we would use the t-tables rather than normal distribution because n is quite small. And you just have to say that kind of thing in words. Good. The next one then is about a field split into 8 plots of area. And you're thinking about the fertilizer and the wheat yields you get out of it. Some statistics are given here. PMCC, well, that's just given in the formula book. It's this one here. I've got the cross term SFW. I've got one of the other ones, but I don't have the other. So let's work out SWW, I guess. We can just use this formula for that. So it's going to be this one here, take away this one all squared, divided by 8, I think is the number here. We put that in a calculator, we get this. And so then, of course, we can just do R is this one divided by root of the two here. And we get this here, apparently. That's quite a strong linear correlation, although it's interesting, you have to put this into context. So rule of thumb, always just write context. That's because sometimes you don't have to, but you'll get it anyway. And sometimes you do have to, and if you don't, you won't get a mark. So just write context every single time. Find the equation of the regression line. Again, this is more stuff from the formula book. So we can say B is SXY over SXX, and now the X is going to go, is usually next to the B in this formula, so that will be the F1 here. So let's do this one here on the bottom of this, and then the cross term on the top, obviously. That will be B, which will be this, and then the A is mean of Y minus B mean of X. Now the X, we've already said, is the one that's behaving like F. Let's do the mean of F, well, that's just 28 over 8, and the mean of W is obviously 303 over 8. And we get these two, so that one's the X bar, so that goes next to B, and that one's the Y bar, so this is going to be A. And then we get A as this, and then we can put it into our W equals A plus BF using these two numbers, and we'll get this here. And then it says, what's the decrease in yield if the amount of fertilizers decreases by 0.5? Well, if the amount of fertilizer decreases by 1, you lose 6.42. That's literally what this equation says. So if it decreases by 0.5, you just lose half of this, which is 3.21. And then we have this plot which shows the residuals. So this is like how far off each one is. So like when F is 1, you're this far from the prediction. When F is 2, you're this far away. And when F is 3, and this far away. Now, what's interesting about this is that the residuals are all positive and like this when you're below 5 and whatnot. And as you increase, apparently the residuals are all negative like this. Now, if this was actually a linear relationship, you'd expect the residuals to be up and down either side kind of randomly, but they're not, right? They're clearly following this kind of quadratic-esque distribution. And so this is suggesting that a linear model isn't suitable because it's suggesting that the further along you go from F, the more the residual is just going to go massively, massively negative, and therefore you should be using some other model to do this, like, for example, some kind of curved model and not a linear model, which is all you have to say for this last mark here. Good. Question number 3 then. We're growing two types of plant, and we want to know what, to a 10% significant level, what the variances of the two different types of potato are the same. Got a few things to do here. Of course, we've got to set out our hypotheses. So we'll say that the variances are the same for H naught, and then they're not the same for H1. It's a two-tailed test, of course, so we're going to go down to 5% when we look at our thing. We're going to need some unbiased estimates, as we talked about previously in the question, because we don't have the variances here. Now, this is the only formula that's given in the formula book. However, it's not amazingly useful when you're given this information. So you might want to go into the exam having memorized this formula for it instead, because we can just actually just use these figures right here, can't we? Because, of course, we can get x bar by just doing this divided by 25, and y this x bar for b by doing this divided by 26, which is essentially what I've done. I've just put them straight in the formula rather than working them out separately. Of course, n minus 1 is just this minus 1 for each of them. This is on page 171, by the way. You get these two figures here, and now this is going to follow an F distribution, where our degrees of freedom for one of them is 24, and the degrees of freedom for the other is 25. So we look in the table, and 24 is only given in the first one, and 25 is the last thing given to you here. Like I said, this is a two-tailed test, right? So we halve 10% down to 0.05, and then we'll be looking at this figure here. So that's the test statistic there. And now when you do this, this is the one when you're doing SA squared over SB squared. This is the one that needs to come to on the top of the fraction where this 24 came from. And the 24 comes from A because that's 25 minus 1. So this one needs to go on top, and then this one needs to go on bottom. We divide them through, we get this. And of course, this is significantly larger than the test statistic that. And therefore, we're in the critical region, and we're going to reject H naught. And then, like I said earlier, just always add some context. So there's evidence that the varieties, maybe I should say, or the variances of variety of potato are not equal is maybe something to say. State an assumption that you made. Now, it's actually given in the formula book here, is that this whole thing we did here of Sx squared over Sy squared is distributed with an F distribution, which is essentially what I did all of this for. That only works if these two things are normally distributed, right? So we're going to say that the yields of the two different types of potato are normally distributed is the assumption that we made here, because otherwise we're breaking this key rule that's in the formula book for us, and it won't work. Good. Question 4 is the obviously the best question on the paper because you actually get to do some proper maths. We've got a cumulative distribution function here, and we're showing k as a half. Well, if you put in x as 2, you need to get 1 out of this, because this is going to have to be continuous. So just set this equal to 1 if x is 2. So f of 2 equals 1 essentially is what I'm saying here. And when you do that, you'll very quickly get k as a half, and we'll get our 1 mark for doing that. Anyway, showing you're working clearly, use calculus to find this and this. Always go to the formula book. This is all the information they give you about continuous distributions. Now, e of x is the integral of x times f of x, but f of x is little f, which is actually the not this big F, right? It's the PDF, not cumulative distribution function. So we're going to differentiate this first to get little f of x. K as a half, remember, and then I just differentiated these two things to get this. And that's little f of x, and now I can actually integrate that again, but with the x attached, and that will give me e of x. And I'll integrate between 0 and 2 because those are the two bounds here that I've got. And this integration doesn't go too badly. It's I think I multiplied these two things first, with the x, of course, as well. And I also factorized out a power of a quarter, or just a quarter here, just to make that a nice whole number. Anyway, this is not too difficult maths. You eventually get this, and that'll be e of x. And then the mode of x is slightly more interesting. There's a few different ways you can do this, but I would always start by trying to draw f of x, because the highest point of f of x is the mode. So if you could just find that, you're done. Now, this function is not the easiest thing ever to draw, but we can find its roots first. Of course, if you set f of x 0, you just get either this is 0, so x is 0, or this is 0, whereby x would need to be 2. So it's got roots at 0 and 2, which makes a lot of sense because of this, right? So it's going to rise up at some point and then come back down again. So where does it turn? Well, like I said, the mode is where it's highest. We can just think about f dashed of x and set it to 0 to find the stationary point. So I'll differentiate this, which I think gives me this. It looks like it does, which is good. And then I can set that to 0, and of course factorize out the x, because x is 0 is going to be apparently a stationary point to start with. And then we get another stationary point here at 12/9, I think, because you just move that over, times by 4 divided by 9, which is 4/3. So there's a stationary point here and a stationary point at 4/3. So I think the graph looks a bit like this. It's stationary before rising, and then stationary up here at 4/3, and then drops down to 0 again. So that's a terrible sketch, because PowerPoint is not easy to sketch curves in. But I think it will do for the purpose of this. And the mode is at that value of 4/3. Now 4/3 is bigger than 1.2, and so therefore the mean is bigger than the mode is bigger than the mean, or the mean is less than the mode. And just have that memorized that that means negative skew. You could also think about this graph here, whereby this is further, this is just past the middle, so there's more stuff over here maybe, so therefore you can say it's negative, but just have that result memorized because sometimes your sketch might be really, really garbage like mine was, and you won't find that easy to tell. Anyway, Alexa believes that the students are equally likely to achieve the same scores in two different papers. All the scores are given here, and we're going to test this. So, okay, again, that's, well, firstly, apparently I just worked out some differences, obviously. So this minus this, this minus this, this minus this, and so on. We get all this. And then you can work out the mean of those differences. So add those all up and divide by, is it 8 of these? Yep, 8. Cool. You can write down your hypotheses, right? H naught says that the mean of D should be 0 because if these tests were equal difficulty, you'd expect, you'd expect some of these to be a bit above 0 and a bit below, but you'd expect the mean of the difference to be 0 if they were of the same difficulty. And if they're not the same difficulty, then you'd expect it not to be 0. So that's my H1 and my H2. She believes this one, it looks like. So that's what we'll be testing. Next, what we'll say is we've got our S squared statistic here. We've used this formula before in this because we don't know the variances of these. So we've used this formula before today. N is given is 8. We already saw that. What we're working out the estimator for the variance of is the D. So we're doing these values here. So this is here is made from 6 squared plus 6 squared plus 12 squared plus 6 squared and so on. I couldn't be bothered to write it all out. Minus 8 times D bar squared. And we've already worked out D bar. Divided by 7 because there's 8 pieces of data. So 8 minus 1 is 7. So we get this value here. And what that means is we can start using this thing here. So for a random sample of n, which is normally distributed, we can use this idea here, right? So x bar minus mu, and we're saying mu is 0 in our h0, is equal to s, which is this thing here, square rooted, I guess, divided by root n. So we're going to have all of this. So x bar is just d bar, it's 4.5, and then minus mu is 0 because of the null hypothesis. And then what I said here, so root of this is s, and then root of 8. And that twiddles a t-distribution of n minus 1. So what we need to do is get out the t-distribution. I think that should have come up slightly, it doesn't matter. So here's the t-tables, and we're going to do 1%, but it's two-tailed, so that's 0.005, I believe, for a value of 7, because 8 minus 1 is 7, and that's this value here. Sorry, this is just what happens when you type this into a calculator, isn't it? And then we're going to measure that against this value, 3.499. But of course, this value is significantly less than that, so it's not in the critical region. And therefore, we are going to accept H naught, and we think that Alexa is probably correct, that there is no evidence that the tests are of different difficulty. Again, writing in some context just to make sure we absolutely definitely pick up the final mark there. Good. Question number 6 is one of those ones where someone's been an idiot and dropped some stuff on their work, and they can't be bothered to do it again, so we instead have to help them out by doing some kind of test for this here. So okay, they're manufacturing bolts. They've got a mean diameter of 5. He thinks it's less than 5, so this is going to be a one-tailed test, it looks like maybe. He's got 10 bolts. We can see some of them here. We can see some information about it, but not everything. We've got a 99% confidence level is this. So that seems like a good place to start. Write down our hypotheses, obviously. So H0 is that mu is just 5, and H1 is that it's less than, because that's what he's saying there. When the variance isn't known, which it isn't here, we've seen this before, right? I think I put this on the screen just before. We've got m-1 s squared over sigma squared squiggles, the chi-squared tables. So here are the chi-squared tables, and we have n-1. Well, we know there are 10 bolts, so n-1 is 9. So V is 9, and then this is a one-tailed test with 5% significance. Sorry, with 1% significance, because now what we're doing is we're trying to get these two values out here. So 99% confidence on two-tailed is a 1% of is left over. Half that is 0.5%, which is going to be this value here with 9, and then this value here for this. And what this means is if you 10 minus 1 is 9, and then sigma squared, little sigma squared. What this is saying is this value. Have I done this the right round? Yeah, I have done, haven't I? This value for the variance, which is this thing here, that came about by having the 0.005 from the chi tables. So if we had used this, so we got this value from this one here. Usually you'd do this in the other way around, right? Like usually you'd use this value here and do this divided by this and you get this value, but it's the same way around here. So I've just filled in this lower end here and then got the chi-squared value from here. And of course I've chosen this one here because to be the smallest possible thing here, we want to be at this with the smallest possible area beneath us, which would be this one here, and then the opposite over here, right? So this one is going to be joined up with this one. I didn't actually need to write both of those things out because they give you the same s value when you do this, or s squared value, depending on whichever one you want. So that's where we get that from. And then, of course, we can say x bar is just 48.4 divided by 10, because there are 10 things here, which is this. And now we have this thing here. So now we're actually moving on to doing our 5% test, where x bar minus mu, and we'll say that mu is 5 because that's the null hypothesis, divided by s, which is, of course, root of this over root n, which is 10. So we did exactly the same thing last question, if you remember, is twiddled with a t-distribution, n minus 1, which would just be t9. So we've got all of this. This is exactly the same as we did last question, which equals some number, this, and then we're going to compare that against the t-distribution, which I've already got out here of degrees of freedom 9, 0.05, because it's a one-tailed test this time, which is this, and this value is, or at least the size of this value is bigger than the size of this value, and therefore it's outside of the critical region. Sorry, it's inside the critical region. So Stan's belief is supported that the evidence, again, putting in some context, that the mean diameter is less than 5. Quite a difficult question, I thought, but yeah, cool. Question 7, so we're making two versions of a toy. One is wood, one is plastic. We've got two different distributions here. This is all about chapter 4, in case you wanted to read that really weird, really small chapter. What we need to do is we need to set up a new distribution that's made of the wooden toy minus twice the plastic toy. And what we're going to say is, like, what we're finding the probability of the weight of a randomly chosen wooden is more than double the weight of randomly chosen plastic. So if we set up this distribution here, what we're looking for is the probability that y is greater than 0. Because if a wooden toy is greater than 2 times the plastic, this will be a positive number. So eventually I'm just going to look for the probability that y is greater than 0. However, first I need to find some things about y, because this is a new distribution. I need to find a new mean and a new variance. So the mean is going to be fairly straightforward because it's just the mean, or the expected value of this, mean and expected value being the same thing here, of course, minus 2 lots of the expected value of this. We already have that, right? 2.5 minus 2 lots of this, which makes this. Now the variance, slightly different. Remember, you always add in variances, and you also square. If you've got a scale factor like this, you always square it. So the variance of this is 0.7. Sorry, no, it's not. It's 0.7 squared, right? Because they've given us standard deviation. So this is 0.7 squared plus 4 times 0.4 squared, which is equal to this. So we have that y is normally distributed with a mean of this and a variance of that. And we're, like I said before, we're just looking for the probability that y is greater than 0, because we want this to be bigger than that. Which is, of course, equal to 1 minus the probability of y being less than 0. You could do some standardization here, or you could just put it straight in a calculator with mean of this and standard deviation being root this, of course. And you'll get this number here if you do that. And then, of course, you'll get this number here when you do 1 minus, and we'll have that there. Now we're going to pack n of these and 2n of n wooden and 2n plastic into the same container. The max it can hold is 252. And the probability that we're bigger than 252 is this here. Calculate n. So okay, got a few things to do here. We'll set up another thing, z, which is the sum of n w's from random w's that we've chosen and 2 nx's that we've chosen. Now there's a subtle difference between doing this and doing something like this here, but the expected value of z is clearly just n times the expected value for each of the w's, which is just n times 2.5, and it's going to be 2n times the expected value for the x's, right, which is 1.27, which is going to give me that, so that's fine. Now the variances, we're just adding together a bunch of individual things here, and so the variances don't do this square thing in this case. They do still add up, of course they do, because we're adding all these things, but they don't. You don't square just because you got 2n of these. You don't square that 2n. This is talked about in detail on these 2 pages, and it lays it out quite nicely. But the variance of just when you're just adding a bunch of individual samples like this, you just add in 2n times the variance like this. When you're scaling it up, like the entire distribution up, like 2 times this, that's when you square it like this. Again, it goes through it in a bit more detail here, which is So have a read of that if you want to. Anyway, so yeah, we've just got n times the variance of the first thing plus 2n times the variance of the second distribution. And we'll have this as our answer. And so therefore, z is normally distributed with mean of this and variance of that. And so what we can do is we can say, okay, well, we need to standardize this. Like, I can't just be lazy and put this in a calculator like I did before because I don't know n. So I do need to standardize this. So we'll just do 252 minus this divided by root of this, of course. So that's there. And now, remember, what I'm looking for is I'm looking for the probability of z to be greater than 252, which we know is that, which of course means the probability of z being less than 252 is just 1 minus that, which is that. And now, what I can do is I can find the z value on a standardized normal distribution by just doing the inverse normal function in my calculator with area of that. And I'll find on the standard distribution, I'll find that the z value is this here, which is actually, coincidentally very close. So where I am on the x-axis, if I've got this much area beneath me, is there. And now I can solve for n here. And that's all that the rest of the question is asking me to do, is just can I solve this equation? So of course, root 0.81 is just 0.9. I can then times across. I can replace n or root n with y, I think is what I did. Then square both sides to get y squared as n. And then put that in. And I also rearranged here. So I just put that there, that over here, this there. And then put that in a calculator. And I got y as these two things, just using the solve function in my calculator. Of course, then I can replace the y back with root n. Root n is defined to be positive, so this doesn't work. And then I square both sides of this, and I get n is 49. And that'll be my answer. We've only got one question left, and it's the Spearman's rank question, which is cool. So we've got a hypothesis test first, because when do we ever not? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 things in this. That would be important. Anyway, of course, we need to set out our null hypothesis, which is that the correlation coefficient is 0, or the alternative hypothesis, which is that it's greater than 0, because we're saying that evidence suggests that the higher an athlete's position, the higher the position long jump. So we're looking for positive correlation here. So rho being greater than 0. So okay, well, all we need to do is go to the Spearman's rank coefficient table, and we've got a sample size of 10. Sorry, was it 10 or was it 9? It was 9, sorry, it was 9. And it's a 5% level significance, and we're doing a one-tailed test, so we'll go to here, and that will be 0.6. So the table says 0.6, the critical value. We've got a Spearman's rank coefficient of 0.85, which is bigger than 0.6. That's in the critical region, and so therefore we're going to reject H0, and we're going to say there is evidence that the higher their position in 100-meter sprint, the higher their position in long jump. Again, putting some context in there every single time. Next, then, the price of paper of the positions was mislaid. So it's another one where we're working with incomplete information in some ridiculous scenario. Anyway, so there's disagreement between athletes B, C, and D because apparently they can't remember where they came in the rankings, or they're just trying to pull a fast one. Who knows? Now that we apparently somehow know that there were no tied ranks. I don't know how we know that information, but it's told us there. So we're going to have to figure out where these positions were. Now, what we need to do here is, firstly, we can identify that the position in the long jump that we're missing is 6, 7, 8, I think are the numbers missing. Next, we know the Spearman's rank coefficient was this, and we know how to do Spearman's rank coefficient. It's in the formula book, it's here. So I know 0.85 is equal to 1 minus 6 times the sum of d squared. So let's work out some d's. So we've got 1 here. The positive minus doesn't really matter because we're going to square it. 2, and then 1, and then 0, and then 0, and then 3. So that's cool. So let's work out the sum of d squared. Now, I don't know these d's. That's fine. 1 squared plus 2 squared plus 1 squared plus 3 squared. I believe that's 1, 5, 6, 15. So the sum of d squared is 15 plus something. All of this squared and added together, I'll just call something, x. So I've got, and then of course n is 9, right? So I've got 9 and 9 squared minus 1 here. I can of course fiddle with this until I solve for x, just by multiplying stuff out, and I get x is 3. So I know that the sum of this, that this squared plus this squared plus this squared is equal to 3. Now, these are whole numbers, there's no ties. The only way to make something squared plus something squared plus something squared 3 is just to use 1 squared a lot. These should be 2's, obviously, not 1's. It should be 1 squared plus 1 squared plus 1 squared, obviously. This is technically true, though. I will claim that, but it's irrelevant because what we're looking for is this squared plus this squared plus this squared being 3. The only way to do that is using 1's, because as soon as you use a 2, you get to 4, and that's too much. So I need these all to be 1's, so I need the differences all to be 1's, so I need to put 6, 7, and 8 somewhere in here such that all the differences are 1. The only one that I can put here is 7, clearly, because I can't put 5 there, which means this one would have to be next to the 6, I think, because the 9 has to go next to the 8. And that gives me a difference of 1, 1, 1. And I think that's the only way to do it, and therefore I think I'll have my answer. Just to finish this entire paper then, without recalculating this, essentially contestant H is disqualified, and would that change the rank? Now, contestant H has rank 1 on both, so he's not contributing any difference, and therefore nothing to this. So if you remove him, nothing changes about this. However, what does change is that you go from 9 contestants down to 8. So n decreases down to 8. Now, if n decreases, that means this fraction gets bigger, because when you divide by a smaller number, you get bigger. So this fraction here becomes bigger. 1 minus a bigger number is smaller, and therefore the correlation coefficient will go down. So a decrease in n will reduce the correlation coefficient. And so therefore, the Spearman's rank coefficient would decrease according to all of this. I think that's the whole paper. Thank you so much for watching, and I'll see you next time.